Okay, so we are now talking about right. What do we want to do with this control? We want to change the trim condition, right. So, let us say I want to fly a different speed, no? So I have to somehow adjust this part so that this is equal to W, right. It's not only in level flight, you can also if you look at let us say climbing flight, steady climb, right. So let us say this velocity is in this direction, so alpha is 0, okay. Right. And thrust is along body fixed x axis, right. So if I want to resolve the forces along this body fixed x axis on the z axis, then this L is what? L has to be, now we are climbing, right. So L has to be equal to and thrust is equal to drag, okay. So not only in this level flight condition, but also in other longitudinal flights, you are actually trying to balance out lift with component of weight. Yeah? No, I am assuming that the velocity is along this x axis. So alpha is 0.
W by cos giving the sign component. W by cos.
Which component is going to act in this direction? Okay, W sin gamma, right. All right. So you are getting this, right. We are trying to this is the level flight condition, okay. So if this gamma is a constant, then it's a steady climb, right. I have to balance this lift. This lift has to be at least equal to this, right, to fly this condition. Now one case of this is when gamma is 0 is a straight and level flight condition. Okay, so what I am saying is longitudinal control is required for changing the trim, right, while you want to change the trim, right. Changing the trim is changing this or this, so you have to compensate for the decrease or increase in one of the parameters, right, and we also have to satisfy this condition, okay. So far we have looked at Now we know these quantities so far, right? We found out expression for this dCm over d alpha and for Cm naught, right? And this is giving me, if I want to plot this, one alpha trim, right? If I do not change anything, okay, then this is what I am getting. Now I want to fly at different speed, that means I have to change this CL trim or alpha trim. Now the question is, how do we do that? Right? If you set this to 0, you are going to get right. Now question is, how do you do that? In how many ways you can get that? One is, of course, we started with, right. In the last class we said that we are going to use a flap at the trailing edge of the horizontal tail, which is called elevator, but let us say now we will go into that little later. Change the camber of the wing airfoil itself, right. Wing camber, if you change, this Cm naught is going to change, right. So you can change the alpha trim, right. Alpha trim is, this Cm naught is for the complete airplane, wing, fuselage, tail, okay, right. If you change the wing camber, this quantity is going to change, so that you can get a different alpha trim, right. So that is one thing you can do. And that will have no effect on the stability. Okay, you are changing the Cm naught, you are not changing Cm alpha, right. So it is not going to change the slope of this curve. So you are only going to shift this curve parallel to this original one, right. So how you can do that in flight? So there will be flaps, leading edge flaps on the wing and the trailing edge flap also, which you can adjust. So you get a different camber and you can modify this. So for same static margin or dCm over d alpha, you can get a different alpha trim, right. So that is one possibility, but would you want to do that? On some airplanes where there is no tail, right, tailless airplane, this is what you are going to do actually. You can change the wing camber. So one thing is, okay, it would be wrong to say that it will not have any effect on the stability, because when you are changing the wing camber, you are going to disturb the flow field behind the wing, right, and through the downward storm, this stability is going to get affected, right. When we say that we are changing the wing camber, we are also changing the flow field behind the wing, and that is going to affect the downwash on the tail, and that will have in turn effect on this dCm over d alpha. So stability is going to change. So this means stability change, right. Right. So, we are actually changing this stability characteristics. Second strategy, yeah, throttle. Throttle is a control, right. Let us not talk about throttle right now. Okay. Changing throttle means lot of things happening. Right now we are not we are trying to look at the aerodynamic control. Okay. Okay. Second strategy, look at this equation, what else you can change? How do you change the slope? So, I can change the slope, right, and get different trims, right, different trim conditions. How do you do that? You are changing this, right, everything else is fixed. Now, what is there in your control? This term will depend upon the CG location, right, neutral point location is fixed, CG location is something you can change. So, you can change the static margin of the airplane, and when you change this you are going to change the alpha trim, right. So, that is one possibility. And this you have to do in flight, because we are trying to change the trim condition in flight. Okay. But that is going to have an effect on the stability characteristic, right, both of them actually. Would you want to do that? So, 1 and 2 okay. I do not want to do that, right, I do not want to do that, and that is where we come to the third control that we talked about, that is use of elevator, right. Okay. So, in the last class we discussed how elevator is going to change the camber of the horizontal tail, and that is how we are going to get a change in angle of attack, right. So, if I want to find out what is the moment due to tail about CG when elevator is also incorporated, then and this has to somehow incorporate the elevator effect. Okay. CLT, so I will write this as CL alpha t, right. Plus a change in angle of attack due to the elevator, right. And this delta alpha T is this. Okay. Depends this quantity, which is the change in angle of attack at the tail due to a change in elevator deflection, is depending upon the area of the control surface and the area of the complete tail. Okay, it is called elevator effectiveness, and this depends upon SE. So, platform area of the elevator part, okay. So, only the control part. No? So, you have this tail, and I am only talking about this area. Okay. So, this area plus this area divided by this total area of the tail. This parameter is going to depend upon the ratio of the two areas. Okay. It varies something like this, maybe it is saturated. Is it all right? Now, let us look at what is the change we see in delta and in the pitching moment because of this particular term. So, what is that change? Into right. Now, I can find out the change in the pitching moment coefficient due to this parameter. Okay. Right. So, this is equal to now change in pitching moment that you can achieve due to deflection and elevator can be represented by this derivative right. So, effective change in pitching moment due to deflection of elevator is this, right. You can properly choose this parameter. You can design your control surface in such a fashion that you may want to have large elevator control power, right. So, this term is called okay. Anything else you see here? Similarly, we will also have a change in lift, right. So, through this terms. So, I can say delta CL due to elevator is going to be, so let us write the expression for this total lift first, right, and this is half rho V squared S plus CL alpha tail into alpha tail, right. And alpha tail is now slightly modified, is not it. So, delta L that you can get through this term is half rho V prime squared into, right, because of elevator deflection the change in total lift that you can get. So, I can also write this as change in total lift coefficient, and that is going to be CL alpha T is 80, right. So, change in total lift due to change in elevator deflection can also be given by this derivative, okay. So, what are we doing finally? We are actually adding a term here which was not there when elevator is not there, elevator is 0, then I get this. When I add the elevator, what I get is right. So, this is the new expression for the CMCG. Is it making any sense? Is it all right? Yeah. Any question? Now, I have a relation, okay, relation which is telling me, no, if I set this to 0, that is the trim condition. No. So, now if I want to find out what is what should be the elevator for a particular alpha, right, that relation we can find out from here, and this is without affecting the stability, isn't it? Do you see that? For stability we had to take the derivative of this with respect to angle of attack, isn't it? This quantity is not going to change, it is only going to change when you apply elevator, right. It is not going to be dependent upon the angle of attack that the aircraft is going to see, isn't it? So, this is not going to affect the stability of the aircraft, right, but what is it going to change? If it is not changing the stability, what is it changing? It is changing the Cm naught, right. Anything here which is not changing in alpha, I can always add that part to Cm naught. So, that is changing Cm naught, but it is not changing the stability, right. So, this is where there is an advantage of using this elevator. Many airplanes where you do not see tail, okay, there are airplanes where actually they change the CG to change the trim, okay. But definitely it comes with other considerations, like the one probably is this Concorde, which used to fly earlier and it was taken off, right. There they used to change the CG to change the trim, but of course it was a supersonic aircraft. So, there would be some other issues there. Okay, so let us try to find out what is delta E trim required for getting any particular alpha trim. Okay. So, clearly it is going to change the trim, but not the stability, because this part is only going to add to Cm naught. So, if you want to draw a corresponding Cm alpha curve, and you will see this. Now, can you tell me if this is for delta E 0 neutral, for what delta E you will get this curve and for what you will get this? Remember this is a negative term, right, minus, no, it is going to change Cm naught is minus negative term. So, what delta E up is negative, okay, down is positive, and this convention has been adopted only to indicate that Cm delta E is negative, okay. So, delta E down, that is going to give you lift up and that is going to create a pitching moment down. So, Cm delta E is negative, isn't it? So, this curve is for what delta E? So, convention is that up is a negative delta E. This one is bringing this down, right, changing the Cm naught by a negative quantity, right, yeah. So, delta E is positive, so it should be down, right. Okay. Let me write another expression. So, I can also write CL trim, right. CL trim is CL alpha into this CL alpha is for the whole aircraft, right, plus okay. So, what is alpha trim? So, now I can write this delta E trim in terms of CL trim, okay. That expression is thus. Let me also take derivative of this with respect to CL trim, so that you get isn't it. So, you clearly see here that this term is going to be dependent upon the stability again, right. It is going to depend upon the stability margin that you have, and this helps in locating the neutral point location on the aircraft in flight. Okay. Let us just look at this formula. I am going to use this. this is one test that you are going to do. Okay, when you are going to go for flight test lab, there is one test you have to do. Okay, let us try to now fly the aircraft at different speeds. So, we will know how much elevator I want at trim, how much CL that is going to give me, and so let us say you are flying one speed. Okay. So, one CG condition, CG is fixed, that Cm alpha is fixed, right, and now I am flying one velocity. So, I am at this delta E trim, this CL trim, change the speed. Another point, right, one more change in speed, V1, V2, all trim values. Okay. And for one CG location you can actually find such a curve, right, change something on the aircraft which will change the CG, and then again fly 3 different velocities, speeds. Okay. So, you get 1, let us say 2 and 3, and you can join these. Okay. V1, V2, 3 different trim speeds, right. Another CG location, and then you get this. So, for 3 different CG locations I have flown 3 different speeds. So, you get corresponding delta E trim and CL trim, right. That is how we have obtained these 3 curves. Okay. Now, I can find out the slope of each of these curves, is not it. I can find out d delta E trim over d CL trim from these curves. So, now I am plotting remember I said neutral point location is the location of the center of gravity, right, where Cm alpha becomes 0, is not it, and Cm alpha becoming 0 also means this slope going to 0, right. If I have the knowledge of how this is going to change with CG location, then I can find out where the neutral point is. So, now I have done this 9 experiments, I would say, okay, for 3 different CG locations. I have found the slope, and I am getting 3 values of this quantity, right, and passing a line through these 3 points, extrapolated is going to cut this x axis somewhere, and that is the location of the neutral point. Because at this point Cm alpha becomes 0, right. So, that is how you are going to find out neutral point location in flight. Now, how is going to be different from the one we found a formula for the neutral point location, right? Is that going to be different from this one? That was an estimate, remember that, right? What that was at the initial design stage. Now, you want to find out whether that neutral point location was correct or not, you have to do this experiment. I want to stop at this point.